So we have covered earlier different format. We have touched the R format. We have also explained the I format. Now we would like to show the J format. J format can be used as an example when we have a jump or a jump and link command. In that command, the very first 6 bits from the left, or the most significant 6 bits from the left, is this for the opcode. And this is common with all the formats. If you recall, with the R format, with the I format, with the J format, all of these, the very first 6 bits are for the opcode. But interesting, in the J format, only all the next bits will be taken as an address, because basically in the J format, I have only to know 2 information. What's exactly the command, which will be jump or jump and link or whatever the thing, anything else. This will be known for the opcode, and then where to jump. And where to jump is not but an address. That's why I don't need actually a lot of information as I had with the R format and with the I format. And the good thing about that it gives me a huge number of bits for addressing. And that's why now I can use, if I would like to go far away from where I am or far away to a certain address, I can use actually the jump address easily in this particular case. So back to the branch addressing, we would like actually to give some hints on the branch addressing that would be helpful for us moving forward, especially when we would like to address a certain particular place. So again, with the branch, we have an opcode, we have 2 registers, and we have a target address. So this is what is usually the I format, opcode, the first 6 bits, and then RS 5 bits, RT 5 bits, and then the very last 16 bits, I can use it as a constant or as an address. With the branch address in particular, I have a target address, which is program counter plus a branch address. So let's go a little bit on details with an example, so we can touch base on how we can basically address a certain particular label in a branch address command or in a branch address command when I use it basically in I format. So let's go through this example step by step, and let's understand how we can map each of these to the format of my basically command. So with this very first one, I have shift left logic. Shift please S3 by 2, and then put the results in T1. So I will look first at the table with the shift left. I should find in this table that the opcode is 0 and the function is 0. Again, this is not but R format. I already knew that as soon as I see this command. Shift this by 2. So I will go to S3 and see inside the table what S3 refers to. I found that it refers to register number 19. That's why it is 19 here. Then I will shift it by 2. That's why I have it here too. And then the results will be in T1. When I look at the table, I will find that T1 is basically register number 9. That's why I will allocate 9 here. If you recall, this is opcode, this is RS, RT, RD, shift amount, and then function. As you can see from here, that we didn't use that guy as an RS, instead we use it as an RT, and we have highlighted that earlier. So basically, when I have a shift left or shift right, I don't use the first source, instead I'm using the second source. And this is the default in this particular kind of process that we are studying. So we understood how to map this to that. With the addition, I would like to add this to that and then put the results here. Again, with the same concept, I will go to the table and see like what is the register number of S6. I will find that the register number of S6 is basically 22. I will go to the T1. I will find what is the register number. I will find that this is 9. And then I will go to the target register or the destination register. I found that, again, this is T1, it is 9. That's why it is here. If you recall, this is RS, RT, RD, as we mentioned. So now we filled all of these things. There is no shift amount, so actually I don't use that at all. But as soon as I have an add, I will go to the opcode. This is an R type. I know that this is 0, and I will find also in the table that the function is 32. Load word is an I format. As you can see from here with this I format, opcode, RS, RT, and then a certain particular shift. This shift here is 0. That's exactly what I have here, the 0. T1, I look at the table, I will find that T1 is basically 9. So I have here the 9. T0 is the 8. I have here the 8. Load word, when I look at the table, I will find that it is 35. So I will allocate here 35. So all of these things, we have already taken examples for that. And it's just a review for whatever we have covered earlier. The new thing that we would like to learn here is the branch and the jump, and how we can use that address. So branch not equal T0, comma S5, comma exit. So we would like to check if this is not equal to that or not. If it is not equal, please go to that particular address. And that particular address is exit, which is here. This guy here is in that particular address. This guy here is in that address. This in that address, and so on and so forth. As you can see, we are just counting by 4. Why we are counting by 4? Because we have the assumption that my memory width is just 8 bits. However, I have 32 bits actually to fill. If I have 32 bits and the width of this is 8 bits, so of course I need 32 divided by 8 slots. So 1, 2, 3, 4. So I need actually 4 slots to fill out all of these 32 bits. And that's why if this is my first 32 bits, the next 32 bits will be plus 4. This here will be plus 4, usually like that. But this in that condition, when the width is 8 bits. If the width is greater than that, then I have to do the math. If this was not 32 bits, again, this I have to do the math, and so on and so forth. And we can play with these numbers, by the way, but the concept is exactly the same. So with that, I'm just adding, with that examples, I'm just adding by 4. So I will check if this is not equal to that. I will go in the table to see what is S5. I will find that S5 is 21. I will allocate here 21. T0 is 8, so I will allocate here 8. And then the branch not equal, I will look at the table. I will find that actually the opcode is 5. Then now I would like actually to write here a number, and that number is pointing out to that particular address. From here, that address is here. So it is that. So here it is written 2. The question is this correct or it is not correct? And if it is correct, why I wrote 2, not any other number? So the answer basically that 2 is correct. And why 2 is correct? Because what we would like to go is this address, which is that address. And 2 means that it is 2 words after the next address. Or in another sense, I am adding the program counter address plus the shift. And the shift is 2 words. 2 words means 8 bits or 8 bytes, 2 multiplied by 4. Because 2 words. 2 words meaning that I will go 1 word. So this is 1 word, and then is another word. So it's basically program counter plus 2 multiplied by 4. When you do that, this is 80,016, and 80,016 plus 8, you will get the 80,024. But by the way, this was actually mentioned. I just mentioned, but you haven't taken that into consideration. I just mentioned that the target address is the PC program counter plus the branch address. And that's exactly what I have here. So 2 is 2 words. 2 words. Okay? So what is the program counter? Program counter is always, by default, points to the next instruction to be executed. So as soon as I am here, my program counter actually is pointing here because this is the next instruction to be executed. And if I'm pointing to the next instruction to be executed, I have to refer to that by the 2. So it is 2 words from my program counter. The program counter now is here. So I need to have 1 word and then another 1 word. Or you can think of this, as I mentioned, 2 multiplied by 4. So I will just add 4 and then another 4, which is a total of 8. So this is a relative address, as you can see, with the branch. Okay, then I will have the next command add immediate. So S3 plus 1 will update the S3. I will go to check where is the S3. It is 19. The 1 here is just the constant. It is 1. And then we will update the S3 how this is, both are just the 19. And the add immediate is basically the opcode here from the table. It is 8. Then the jump loop, this is the address of my jump. But then I checked the table. I found that actually the opcode is 2. But then I have here the 20,000. But with these 20,000, I am referring to the loop. But loop address is 80,000. So I have to write here a number that will let us know that basically I am targeting that. But since we are saying that now each word will have like 4 slots, so suppose if this is the case, I need to multiply that, of course, by 4. So this I will know that address, or divide this by 4. So this I know where is exactly to write here my number, or what's exactly the number to be written. But this, in case I have 32 bits and I have my memory as an 8 bits. But suppose that I'm giving you like a 64 bits, for instance, then you will count by 8 instead of 4. And you need to think accordingly for the number that has to be written there. Then my exit here, and this will be my address. So as we have seen, the branch address is just a relative address. But suppose that we would like actually to branch far away from my address. It is a relative address, correct? And suppose that I would like to go to an address that is basically far away from my location, very far away. Okay, that's fine, very far away. You already mentioned to us that you have the opcode, you have RS, you have RT, and then you have total of 16 bits to use it as a relative address, correct? But what I am saying here, that it will be very, very far away, that number actually will not be fitted only in 16 bits. That number is too large to the extent that I need more than 16 bits. How I can go over this problem? What is the trick that I can do in order to solve such a problem? Again, the problem is I would like to go to a certain address, to branch to a certain address, which is far away from me. Far means that that number should be written in greater than 16 bits. However, I have only 16 bits. The idea is simply like that. Suppose that I would like actually to branch to this L1. And also assume that this L1 is actually too large. So it can't be written in only 16 bits. It needs actually more than 16 bits to write the L1. Branch equal, if this is equal to that, please go here. But this is, I can't write in 16 bits. The alternative way actually to do this trick. So I would say branch not equal. If this is not equal to that, please go to the next instruction to be executed, and this is L2. Suppose that L2 here is here. This is just the next instruction. Of course, I don't have to have it as an L2 here, since it's just by default to go to the next instruction to be executed. So if they are not equal, which means that this is not satisfied, if they are not equal, please just go to the next instruction to be executed. In this particular case, it's just L2 here. But if they are equal, I will go to the next instruction to be executed. And what is the next instruction to be executed? Jump to that particular address, which basically I am targeting. The nice thing about jump that this address now can be written in all of these. And this is, of course, a lot larger than my 16 bits. And by doing this trick, now I can go to a far place from my address with this trick. Okay? So now we have seen like different type of addressing modes. Let's like touch them a little bit in detail so we are aware of like how we would basically address all of these modes. Just the idea of addressing mode is just the way of specifying an operand or a memory address. So either an operand or a memory address. If you have seen when I'm saying like add S0, S1, S2, I'm not in particular adding S2 as a number. Rather, I am adding whatever like the address in S2 plus whatever in the address of S1 as a register and so on. So I'm adding the slot, let's say 7 with a slot 8, and then put the results in another slot. So this is like as an example of a way of addressing. Also, we have some examples with the I type. For instance, I have add I, which is using an immediate addressing mode, or a branch equal, which is program counter relative addressing mode, as we have explained, or load word uses base addressing. Let's go a little bit even more in detail. So these are the addressing modes. Immediate, it's just a numeric value embedded in the instruction in the actual operand. Register is, as an example, jump register, and it just like have a source or destination operand, which can specify a certain particular register location, and then you are actually implicitly telling an address. Program counter relative, it's not but whatever we had with the branch equal and the branch not equal. Base address is the example that we had earlier for the load word or store word, meaning that you have an address that is written in a certain particular slot register, and then you add to that address a certain constant. This is what we refer to as a base address. Pseudo direct instruction, it's not but how we would do that with the jump instruction. Okay, so suppose that this is just like the highlights, but we still did not understand that in details. Let's go further in details with whatever is explained here. Again, register addressing. This is an example, add S1, S2, S3. What's exactly I'm referring to? Please go to that particular location, S3, inside my register. You will find a number there. Add it to another slot that is actually in S2, add both of these, put the results in S1. So this is what is basically the idea. And this type of way of addition, for instance, is called register addressing because the address is already written in the register, correct? I'm just telling you what to add by telling you the address of the slot. Then instead of telling you like, please add 200 plus 100, I'm telling you, please go to slot number 7 in your register. Yes, address, correct? Slot number 7. 7 is an address, it's not the value. Go to slot number 7, add it to whatever in slot number 9, and then put the results in slot number 10, for instance. So all of these, I'm just giving you an address. And that's address inside the register, and that's why we refer to that as register addressing. Another address mode is called base addressing. An example for that would be load word or store word. Of course, I am telling you, please go to that particular address. How you will go to that particular address? You will go to slot number S3. You will go see the table, where is S3? So this is my slot. Suppose that this is S3. You will read the value that is there. And then you will add 32 to that particular value. Then you know exactly the new address. We refer to that as base address. You just would like to target a certain particular place inside the memory. And I'm giving you by two values here. One inside the register, and the other is just add a certain particular constant, and we refer to that as base address. The same example, of course, with the store word. Immediate addressing. An example of that, let's suppose that we would like to do an add immediate. Immediate 0 plus 7, put the results in S1. So I'm going to register 0, see what is inside there. Of course, it is 0 plus 7, and then put the results in S1. This is what I called immediate addressing. Program counter relative addressing, it's just whatever we mentioned for the branch. The program counter plus a certain offset. So program counter plus a certain offset, it will give you the program counter relative addressing. It's exactly the example that we just solved a couple of slides ago. Pseudo direct addressing, this is for the J format, and you are concatenating the 4 most significant bits of the program counter with a certain bits of offset inside the J format. I don't want you to know further of information for the J format more than that, because we will touch this again with the exact concatenation with which exact bits little bit later when we go to the data path, and we will go deep into all of these things to see how we can actually create that particular address. Furthermore, let's go over this again as a review. With immediate address, you just have an immediate address here. With the register addressing, I'm telling you, of course, what is the RS, what is the RT, and where to put the RD. So all of these is just a register address. Base addressing, I'm giving you a constant here with the load word or store word. And this constant has to be added to a certain particular value inside a certain particular slot inside my register. Adding both of these, then you know where is exactly my address inside the memory. And this, we refer to that as base address. Program counter relative is just whatever we mentioned in the branch equal and the branch not equal. You have the program counter address, which is the next instruction to be executed, plus the offset that I had, which was 2 in my example. This plus that will show you the exact address in the memory, and this is program counter relative address. With the jump address is something similar. You take that address, but instead of addition, you are concatenating with the program counter in a certain way that we will explain later on in the course. After doing this concatenation, you will point out to the correct location inside my memory. And these are the addressing modes. Of course, it is expected that you will be familiar with all of these addressing modes and examples of that. Let's take that example. It's written in a high-level language, and it's basically a swap example. So this function is written here in C, swap. I have an integer of array V and then integer K. What I would like is to swap a certain particular location inside my array. So basically, I will have this, my memory as an array. And there is a certain particular location here. I have V of K. Of course, the next one will be V of K plus 1. What I would like is to swap this between this and the other one. So whatever in VK will be here and whatever in V of K plus 1 will be there, just a swap. So how we do that? Of course, we need to create a certain temporary register. This integer temp, so I am creating now, initiating a certain register, a certain variable called temp. I will save inside this temp whatever I have in V of K. So now V of K is in temp. Then I can overwrite whatever in V of K right now, since I have already saved the V of K in a temp. So I can overwrite whatever in V of K with the V of K plus 1. So now I have swapped one of these things. That V of K plus 1 now is inside V of K. But how to update V of K plus 1 with the data that is in V of K? So the V of K plus 1 will be updated with V of K by just having the temp register. So this will be equal to temp. V is in A0. Of course, this information I should know you already in advance. I don't have to give it to you. Why? Because this is the first argument and this is A of 0. So this is basically here A of 0. The second argument, K, is in A of 1. Of course, this will be A of 1. And also, I don't have to give you this information. This is just information that you should be aware of yourself. And I have temp in T0. So this register temp, I am saying that this is in T0. Also, this information I don't have to tell you because you can actually assume it by yourself. You can assume that I will create a register called temp, and this temp, I will refer to that as the slot T0. Another one would say like, no, this is will have T1. Another one will have T2 and so on and so forth. But the concept at the very end would be the same, correct? And this means that, of course, the solution between one to the others will not be exactly the same. So given all of this information and giving you only this code, then without any of these, you can still write your assembly code. So the problem here again, I have my memory. And as we mentioned, this memory is 8-bit by default, unless otherwise specified. And V of k will be like a certain space here. I will have my V of k. But the issue that I know that this is an integer, V, so the array integer, so I know that it's 32 bits. 32 bits, and this is 8 bits. Of course, I need 4 slots. I have 32 balls. I need to fill out in slots. Each is basically 8 bits. So how many of these? I need 4. 1, because 32 divided by 8 is equal to 4. So 1, 2, 3, 4. So V of k will take all of these 4 slots. That's V of k. Of course, I'm expecting that the next 4 slots will be V of k plus 1. 1, 2, 3, 4. All of these will be V of k plus 1. So basically, V of k plus 1 will be here. So what I would like is actually to swap. This is here, and basically this is here. Unfortunately, I can't do that directly inside the memory. I can't do that. This type of processors, I can't do like operations directly inside the memory. What I need to do is what? What I need to do is basically move this or copy this V of k to a certain slot here, and then copy V of k plus 1 to a certain slot here. So this is now V of k. And this is now V of k plus 1. And what I need to do is doing the swap, meaning that whatever is here in V of k will, so of course, going from this to that, it's load word. Going from this to that, it is load word. Now I would like to do the other way around. So this V of k by store word, instead of having this here, it will be going to that V of k plus 1 by store word. And then this guy will be going to here again by what? Store word. This is the idea that I am targeting. Correct? Let's see that in the assembly. But before that, there's a very important also aspect here I would like to highlight. That the very first step is to know what is the address of V of k. Correct? What is the address of this? Because this is what I would use in my load word command. Because load word, I have to load from a certain particular location inside my memory to a certain particular location inside my register. So first of all, I need to know the address of my array inside my register, correct? Sorry, inside my array. So this will be the very first thing to do. The other important things to know also is what is the address of the next instruction. So first, what is the address of my array? And what is the address of the very next instruction? Of course, as we mentioned earlier, since we are counting by 4, that's why I have always to multiply whatever the I of that particular array by 4. And then add that to the base address. What does that mean? Back to the houses example. Suppose that I have a street which have like many houses. And suppose that we are adding by 4 to address each of these houses. The very first house is address 200. The one after, of course, I'm expecting 204. The one after is 208, yes? So you can think of this, that house of 0 had the address of 200. House of 1 had the address of 204. House of 2 is 208, correct? How I did know that 208 is house of 2? It is 2 multiplied by the increment value, which is 4. 2 by 4 is 8. 8 plus the base address is 200, so I get the 208. I can do the exact same things with the 5th, 9th, 10th, multiplied by 4, add to the base address. This is what I need to do, the very first step. Multiply by 4, and then add to the base address. How I will multiply by 4? This is V of K, correct? This is K. K is in A1, correct? By default is in argument 1. I know this information. So I have to multiply A1 by 4. How I multiply A1 by 4? Shift left by 2. Because shift left by 2, the A, it means that it is multiplied by 4. Please save this new number in T1. So now in T1, it is not but A1 multiplied by 4, or I multiplied by 4, if we refer to that with the example of the house. Then I multiplied by 4. The next step is to add to the base address, add to the 200, yes, the base address. So I need to add this T1, which is here, to my base address. What is the base address? It's the very first house. In this case, the very first house is what is referring to this as A0. Since V here has the A0, it's just pointing out to the very first address of the array. It's addressing actually the V of 0. So this means that I will add this to that. Please update now your T1 with the base plus K multiplied by 4. So now I know the address. Now I know the address of the house. I know that it is 208, for instance. So please go to 208, bring the stuff from there, and copy it to a certain particular place inside my register. Please load Word from that particular address. Suppose that it is 208, it is T1. There is no base, there is no shift. It is that 208, there is no shift, it is there. Please copy that to T0. So now what I have done, that I went to the correct address, this guy, yes, and please copy that to my slot T0. So inside my T0 now, I have V of K. V of K is here right now. Then I need to refer to V of K plus 1. This is V of K plus 1. V of K plus 1 is not but this address by shifted by 4. Same address as this one, same address, but shifted by 4. Please go and bring that, put that in T2. So now I have in slot T2 V of K plus 1. What I'm supposed to do next? What I'm supposed to do next is not but, please, this store word into that place, and this store word into that place. The other way, I would like to shift to the other way, swap. If this is the case, I know that this now I know now that this has the V of K, this has the V of K plus 1, and this is in that, and this is in that. What I need to do is the other way around, this here and this here, but by store word. So store word T2 to this, T2 to this, and the store word T0 to this, T0 to that. Swap. Yes? I just swap the addresses. Correct? And then after I finished all my jobs, what I'm supposed to do? Say exactly the same thing with the example that we mentioned with the shopping. After when I park my car, I have saved the address to where to return. I have done with the shopping. What will be the next step? Look at my mobile or the address where I was already written the garage address. Please go to that address. Here, jump register to return address. Since this is swap, you finish the function. After you finish, please go to where you were inside your code. That's why jump register with the return address register. So with this simple pseudo instruction, we have taken something like that before with the move. T1, T0, T1, meaning that I am basically copying whatever is here to that. This can be written as add 0 plus T1, put the results in T0. This is not but moving whatever or copying whatever is here is there. Branch less than this or this to 1. We have shown before earlier that how to actually decompose that particular pseudo instruction to the basic instructions, as you can see from here. The most important thing that we are using an @ register is a temporary register that is basically register 1 inside my register slots. So we'll switch the gear now to the arrays and the pointers. We need to understand what are the differences between them and why one is better than the other in terms of many aspects. But before we go deep into that, here is just like an example that is basically written in the normal way with an array. The same example is written in the pointer idea. That particular example is transferred to an assembly here, and that one is also transferred to the assembly here. By just with the first glance, if I were to ask, or if I were to think which one will be more computationally efficient, or which one could either this or that will be much faster, which one we should think of basically having a faster execution than the other? So the answer with this, if you look at the loop in that side, you'll find that 1, 2, 3, 4 instructions, but the loop in that side, 1, 2, 3, 4, 5, 6 instructions. So this means that each time you actually loop inside 6 instructions, this guy is only 4 instructions. So if you think of this at the very first step, it's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the very first step, both are the same. However, was just going to the loop. This is just looping 4, but this is looping 6. So of course, this guy will be much more efficient than the one with just the array. But let's a little bit going into details to see why is that. First of all, let's remind ourselves, or if you are not familiar with that, let's define what is a pointer. So basically inside the pointer, you are just pointing to a certain particular address or a unique address that actually has a certain particular variable. So instead of having the variable basically value by itself, you are pointing to an address that holds that particular value. Let's take that example. Suppose that I have a variable, define a variable n rate, and this n rate has the value of 10. So this is the usual case that n rate is equal to 10. So it'll be inside the memory a variable n rate, which has the value of 10. But this is my memory. So earlier we have the memory like that, correct? And this is just like the memory. Suppose that I have actually allocated differently, that instead of having on top of each other, they are just beside each other. And so on. So this is the very first one. This is the second one, third one, and so on. This one had this particular address. So if I would like to define a pointer that is pointing to that address, I will define a pointer called point to n rate. And inside point to n rate, I will hold that particular address, which is that address. So basically now I am pointing to that address, which is holding that value. This is basically the pointer. I will define it that way. Integer, and then the star here, the asterisk, and then the pointer name. By having this like that, so this means that this guy will hold a pointer to a certain particular address. But then I need to know like which one of these. This is what we will explain in the next slide. So again, the variable name is just directly reference a value, but a pointer is indirectly reference a certain value. With defining a pointer is just like with the star or asterisk symbol, but the address of will be referred to as the ampersand symbol. So the address of what? So now I'm pointing to a certain address, which was like the 00A, for instance. But the address of what? The address of what? I will refer to that with the ampersand. Let's take an example here. I will define a variable with integer x equal to 1, y is equal to 2, and then an array z of 10, an element of the array z of 10. I will define also a pointer that asterisk IP or star IP, which is pointing to a certain integer. I am pointing to an integer. But that pointing to an integer to which of these variables, this is what I will do. I will define IP is equal to the address of x. So now I am pointing actually to x, which has the value of 1 in this particular example. So I'm pointing to that. With this %, I have defined where I'm pointing to. Let's take also that example. I have a variable in location. This is n location, and inside n location I have 100. So n location is equal to 100. I will define a pointer here. This is integer, and then the pointer to n integer. I am pointing to a certain integer, which I know that I would like to point to that one. So I'm telling you that this guy is pointing out to the address of n location. And that's why this value will be here. Because I'm pointing out to the address of this variable. Yes, so it is a pointer. Yes, it points to an address, but to which it's pointing to an integer, but to which integer? That's why I have defined it here. Okay, so why all of these basically useful? Let's going back to the same example that we had at the very beginning. Let's try to go over this step by step. With this, it's say like, okay, this is integer array, and then size. Of course, this will be in A0, this will be in A1. And then loop for I equal to 0. If I is less than the size, please increment by I. And then in all of these cases, array of I is equal to 0. Meaning array of 0 is equal to 0. Array of 1 is equal to 0. Array of 2 is equal to 0. But with each of these time I'm adding a 0 or moving a 0 to that particular array element, I need to check if the I is less than the size or not. At the very beginning, I just need to put array of 0 is equal to 0. And from that moment, then I always check the size, and then we'll do that. Again, I have to allocate I is equal to 0. So I'm telling, okay, please move 0 to that particular location T0. And I already decided myself or yourself that I would be in T0, and now it is equal to 0. Okay, so I begin with I equal to 0. But then I would like to allocate a rule that always I would be able to get the address of my I. So what is the address of array of 1? What is the address of array of 2? What is the address of array of 3? What is the address of house of 0, house of 1, house of 2? The same exact rule that we mentioned. Multiplied by 4, add to the base address. Multiplied by 4 and add to the base address was 200 in that particular example. Then we know the address of that house. It is exactly the same things. What we have done earlier, we will do it again. How to multiply by 4? It is just shift left by 2. So this is I shift left by 2, put the new results in T1. So T1 now has the I multiplied by 4. Next, add that to the base address. Base address of what? Base address of my array, base address of my house, correct? Base address of my array, which is address of array of 0, which is written here, is written A0. So I will add that, which is this, to an A0 and put the results in T2. So now T2 has the address that I'm targeting. Suppose that I would like to know what is the address of the array of I, which I here in this case is 1. If the array of 0 was 200, then the array of 1 will be 200 plus 4, 204, correct? So now I know 204. I know that 204 is basically pointing out to the array of the I that I am interested in, correct? So now I am pointing to the correct address by the value in T2. So if this is the case, what I need to do is array of I is equal to 0, correct? Array of I is equal to 0. I know now that T2 is pointing out to the address that I am targeting, correct? Please put 0 to that particular location. Store word 0 to that particular location. This is the address that I'm targeting. Please put 0 there or copy 0 there. That's why I store word 0 to that particular location. And then after you have done that, please increment the I. I will be I plus 1. I will be I plus 1. Okay, and then I need to check if the I is less than the size or not. Set less than. If it is less than the size or not, I is less than the size or not. I is here in T0 because I is incremented by 1. So it is here. This is I. Is this less than size or not? Where is size? Size is here. And I know in advance that it is in A1 because this is the second argument. So I will check if it is less than A1 or not. If it is less than A1, and suppose that this is true, I would expect this will be equal to 1, correct? Because if it is true, T3 will be equal to 1. Suppose that this is the case, that T3 is equal to 1, then the next step is to check, is T3 not equal to 0 or not? In this case, it is equal to 1. So of course, it is not equal to 0, so please loop. So I will just loop until that actually will be equal to 0, and then I will stop. Correct? The same exact things we would think about the array. So again, array of 0, move that. So A0 will be to T0. So basically, P will be the address of the array of 0. And then again, I will multiply by 4. So A1 will be shifted by 2, and then put the results in T1. And then I will add this T1 to the base of the array, which is A0. And then now I look at the T2, which is pointing out to the address of the array of my size, which you can think of this as my point or my array that I'm pointing to. Okay, so that's fine. So now I'm pointing to the correct array. The next step, again, store word 0 to that particular address. Store word the 0 to that particular address. And then store word the 0 to that particular address. But since I have a pointer that pointing out to that address, the very first of the array, if I would like to move to the next array element, if this was P, this will be, the next one will be P plus 4, correct? The one after will be again P plus 4 plus the updated one, and so on and so forth. So just adding P plus 4 is pointing out to the next address location. And this is what I have done here. Please add I, T0 plus 4. It is T0 updated now, which is P plus 4. So now I am going to the next, basically, address. And then I will do the exact same thing. Set less than, if this is less than that or not, if this is equal to 1, so this will be not equal, and then I will keep looping. But the good thing here that I'm looping only with 4 lines instead of 6 lines.